Hello, biologists. We are going to finish the last couple of slides that we didn't get to on lecture on Wednesday. So please watch this before exam 3. We left off about to talk about the global water cycle. So we know that energy flows through the ecosystem. It's lost at every trophic level transference. It's lost because not all of the sunlight is used for photosynthesis. But water doesn't leave the system, neither does nitrogen or phosphorus or carbon. So water stays on Earth and it cycles. It doesn't flow out like energy does. So this is our global water cycle. And what we want to do is look where the arrows are going and look how big they are. So wherever the biggest arrows are, that's where the majority of the reservoir of water is. And this will be true for the other cycles we're about to look at as well. So the majority of the reservoir of water on Earth is the ocean. That's about 97.5% of Earth's water, which is almost all of it. And we can't drink seawater. It's too salty, it's too salinic. So we have to drink fresh water only, which means majority of the water on Earth is not available to us to drink in the state it's found in right now. Now, most of this water just evaporates, condenses, and then precipitates back down into this fabulous cycle of rain over the ocean. Some of those clouds, though, are going to move on land, and they are going to rain onto the land, which is great for us because we want that fresh water. So when it rains onto the land, it will fall into rivers and lakes and our storage areas of fresh water. And some of it will be evaporated back up and it'll rain back down. But some of it will run down these rivers back into the ocean. It can happen on the surface or it can happen through an aquifer. An aquifer is the space where you find water that's below ground. It's not an empty space. It's more like water found in the small nooks and crannies between rocks and stuff. So that's the water cycle. Majority of it's in the ocean. Evaporation, precipitation, and then running back into the ocean. Next, we have the nitrogen cycle. Now, the nitrogen cycle is pretty cool. There's two reservoirs. One is in the ocean, but the main one, 78% of all of it, is in the atmosphere. And this is actually 78% of what makes up the atmosphere is nitrogen. It's not 78% of the nitrogen found on Earth, but the majority of nitrogen found on Earth is in the atmosphere as nitrogen gas, which is two nitrogens bound together. This is kind of a bummer because two nitrogens bound together is an inorganic molecule, and it's not really usable to most creatures. Like I'm breathing it in right now and it's doing not a whole lot for me. So let's get this nitrogen out of the atmosphere. We can get it out of the atmosphere by having it be sucked into the ocean by nitrogen-fixing cyanobacteria, or we can get it out of the atmosphere by sucking it into the soil with nitrogen-fixing bacteria in roots and soils and from crops. We're going to talk more about that nitrogen-fixing bacteria in just a second. We also can suck it out and use it in industrial production of fertilizers and burning fossil fuels and all that kind of stuff because we're using air to do that. So we're burning what's in the air. This can be a problem because fertilizers and fossil fuels, the fertilizers contribute to pollution, eutrophication, runoff, and burning fossil fuels contributes to our greenhouse gas issue. So climate change is involved as well. And then pollution goes right back out. But luckily that's a thin little arrow. So let's look at these bigger arrows. So nitrogen-fixing bacteria in the soil, and then they release their nitrogen molecules when they're done. Those nitrogen molecules can be used by terrestrial organisms. So they're going to suck it up and let it back down. Nice little cycle here. You also release nitrogen with lightning, which is pretty neat. So this cycle here is pretty impressive. And I want to talk more about this, how this happens by talking about these bacteria. So that's the next slide. This is a root right here. These are little roots. And then these things are called nodules. So these nodules are root material that are perfect little houses for bacteria. So the bacteria live in these nodules and they fix nitrogen. to fix something doesn't mean it's broken. It means you're taking an inorganic molecule and you're turning it into an organic molecule. That organic molecule can be used by other organisms like plants and soil bacteria and animals. And so it's pretty exciting that these bacteria have this symbiosis with these plants. A lot of these plants are in the Fabaceae, so legumes and beans and peanuts and clovers and fabas, all that kind of good stuff. So this benefits both organisms. It's a mutualism. Here, our major reservoir of nitrogen is in the atmosphere. It is an inorganic compound because you need carbon and hydrogen to be considered organic. There isn't carbon and hydrogen, so this is inorganic. This atmospheric nitrogen is going to get sucked up by these nitrogen-fixing bacteria in the soil and in the roots of these legumes in the Fabaceae. And those little critters are going to take the nitrogen, they're going to ammonificate it, which means they're going to turn into ammonia. Then they're going to do nitrification, which means they're going to turn it into nitrates. And then those nitrates can be released into the soil and they can get used by plants. So assimilation means they get sucked up by the plants. And now these plants can use that nitrogen because it's a biological molecule now, it's an organic molecule. They can use it to make their tissues, which means that your primary consumer can eat your producer, and then your decomposers can eat the plants when they die, and that nitrogen can be used for living things. So it's pretty cool, but it has to go through a couple steps to do it. There are also denitrifying bacteria that take these nitrates and release them back up into the atmosphere. So there's this cool cycle here. And when your primary consumer dies, it will be decomposed by our cool fungus friends. And then those nitrates will be released back into the soil. But to get it out of the atmosphere, it's mostly our nitrogen fixing bacteria friends that are doing it for us. So that's why they are so important. In fact, if I were having this live, I would have asked you this learning catalytics question. What is the largest reservoir of nitrogen? Pause it if you need more time. If you've already answered, hopefully you answered A. That is correct. The largest reservoir of nitrogen is in the atmosphere as an inorganic compound. So we need our nitrogen fixing bacteria friends to make it organic so it can be used by plants and then get into the bodies of consumers. So that's why nitrogen fixing bacteria are so important. Let's talk about the phosphorus cycle now. Phosphorus cycle will start with a volcano. It aerosolizes all of these nice phosphorus compounds. They get dropped down into the food web. They dissolve into streams. They dissolve into the soil. Then they can evaporate back up, or they can get leached off into the oceans. And so these dissolved phosphorus compounds move through the oceans, and then they land in sediment, and then they get pushed back up as the continental plates shift. And so that sediment from the ocean is now exposed in rocks in the soils, and that can get dissolved into the streams and go back. So this is a very complex cycle. And note that we're not giving you any of the phosphorus compounds. It is important to know that it's just this circular movement of phosphorus and that volcanoes are involved, but we don't go super in depth into phosphorus. If you do botany later in life, you will talk about how important phosphorus is to different organisms, specifically plants. The carbon cycle is really our most exciting one right now because we talk about carbon all the time with climate change. So the major reservoir of carbon currently is in the ocean. That's where this big arrow is. So the ocean has most of our carbon, and we know that carbon dioxide from the atmosphere that we release by burning fossil fuels gets dissolved into the ocean, and it increases the acidity of the ocean because if you take CO2 and you put it in water, you create carbonic acid, and acid decreases the pH of the ocean, making it more acidic. So ocean acidification, we've already talked about, it's an issue. Anything that does cellular respiration is also going to release carbon dioxide as part of the cellular respiration process. So that's respiration. So photosynthesis occurs. You suck in carbon dioxide to make your sugars. Then you make your sugars and you use them and you exhale carbon dioxide. So plants will suck it in and respire it out, but plants suck in more than they release because that extra sugar that they make, the net primary production, they can store that in their body as biomass. And so like all the wood and leaves and tissue and bark that you see on a tree, the carbon in there that forms those cell walls and all the sugars came from the atmosphere. So they're literally sucking carbon out of the air and putting it into their bodies, and then you and I can eat it, which is pretty amazing. Here's another reservoir. These are two arrows. When I first saw this, I thought it was a weird circle with a Z in the middle, but this is two arrows. And so this is the terrestrial reservoir of carbon. It's you know, it's decently big, but it's not as big as the ocean reservoir. You also can have carbon that just kind of falls down. Arctic snow drifts and lands on the bottom of the ocean, and then will get pushed up through sedimentation, uplifting, and then weathering will drop it back down. But note that these arrows are pretty lightly colored and pretty small. Also, some of it will be buried and will become fossil fuels. And then this is our problem right now. We take those fossil fuels and we burn them. And this arrow is nice and thick and big because we're releasing a ton of carbon dioxide into the atmosphere by burning fossil fuels. And this is industry, construction, electricity, transportation, creating concrete. It's a big thing. And then as we need more materials, we deforest different parts of our environment. And as we deforest, we remove trees that suck up carbon dioxide from the atmosphere. And so it's kind of this positive feedback loop where you cut down trees, so less carbon's being taken up, and so more of it's being released, and it becomes a nasty mess. But we know about climate change already. We should continue to talk about it because it is so important. We have here carbon emissions from burning fossil fuels, carbon emissions on the y-axis and year on the x-axis. So 1400 up to about 2000. And we were not burning a lot of carbon until around the early 1900s, and it's just increased since then. So this is why we're concerned about releasing greenhouse gases. We're just releasing them at a higher rate than we ever have before. And we can track this and see that there's a correlation. The amount of carbon dioxide in the air over time. So here's carbon dioxide parts per million. And here's the year, so it's the same years as above. It's fluctuating and it's increasing. So there's a correlation to the amount of fossil fuels that we burn and how much carbon dioxide is being released into the air. And I mean, it makes sense. If you're burning something that contains a bunch of carbon, carbon dioxide is a byproduct of that use of fossil fuels. Something else that I think is important to know for life, but also for this class and for your exams, is where these greenhouse gases come from. So our most recent data is from 2019, which is 2 years old at this point, but 2020 is going to be a weird year to look at in graphs because our behavior changed so much. So I think this is a good representation of what happened before the pandemic. The major source was transportation. And so when I used to think about transportation, I was like, oh no, it's my car. I should ride my bike. And that'd be great. I could totally do that. But it's also bigger than me, right? This is transportation like trucking network, shipping containers, airplanes, all of those major carbon emitting sources of getting things, goods, materials from one place to the other. And so most of our consumables come to us in these giant shipping containers on massive ships. And so that's also a part of it. We have a global import and export business between all the countries. And so it's bigger than just your personal car, but your personal car, if you drive, does play a role, a small role. The next largest chunk of the pie, so transportation is where we release most of it, is electricity. So this is interesting because there are green options and we're starting to try and invest in them and move toward them. And there's also like community aggregate electricity buying options that you might want to look into. But electricity produces about a quarter of our greenhouse gas emissions. And this is for the United States, by the way. I don't know if I mentioned that earlier. The next heavy hitter is industry. That means production, manufacturing, making things. It's really such a giant category that it's hard to list what's included in industry. It's like making everything. Then you have commercial and residential at 13%. That's building new houses, putting in parking lots, making sure that we have what we need for our society to function. And the last bit is agriculture. 10% is agriculture. And we always give agriculture a hard time because livestock produce a lot of greenhouse gases, but it's also bigger than that. Livestock take up a lot of usable space and a lot of land and a lot of water. So a lot of resources go into livestock, regardless of how much carbon dioxide or methane they produce. So agriculture, even though it looks like just 10% of the emissions, it would be 10% that would have more beneficial impacts if we could start working on figuring out a better way to do it. And that brings us to the greenhouse gas effect. We've talked about this before, but as our last lecture, I just want to make sure that we reiterate it. This is how it works. So solar radiation from the sun goes through our atmospheres and comes to the earth and heats the earth. Now, some of it doesn't make it, some of it's reflected by clouds, some of it's reflected by, the surface of the earth, but a lot of it comes in and heats the earth. What would happen usually is the heat and UV radiation and all of that solar energy would just dissipate back through the atmosphere and leave the earth. But greenhouse gases act as an insulating layer. So these greenhouse gases, they actually block the heat from leaving the earth, much in the way that a greenhouse traps the heat from sunlight. So it just keeps this layer of warm, hot solar radiation on the earth, which is increasing the global temperature of the earth. And we know that leads to things like disturbing climate patterns, so increased disasters, hurricanes, droughts, fires, extreme cold temperatures, extreme hot temperatures, the melting of glaciers, the raising of sea level. Like, it gets really complex really quickly. When we think about these greenhouse gases, we usually think carbon dioxide first. And that's true because 80% of the greenhouse gases being emitted by the United States in 2019 were carbon dioxide. So carbon dioxide is by far the most emitted greenhouse gas. The second common most emitted greenhouse gas is methane. That's that one that cows produce in their belches. Cows are very methane heavy. And then you have nitrous oxide. And the last one is fluorinated gases, gases that contain a fluorine. So carbon dioxide, man, 80%, pretty impressive. Here are our total emissions depending on population size and resource use. And I think it's important to think about it because we always think about the United States first, and we probably should because we are a large emitter of CO2 per capita. So here's the population size. We have China, India, and the United States is the third most populous. Then we have per capita CO2, carbon dioxide, I don't know why I'm trying to say it, carbon dioxide emissions. We are the highest below like Canada here. And then China, and then all these other countries. And then total emissions, this is what we're concerned about. China is the highest based on population size, even though per capita is lower than the United States. And then the second option is us. We are the second highest based on total emissions through capita. So us and China are going to hopefully work together and figure out how to decrease our emissions. The effects of climate change are varied. There's a lot of them. One is that you're going to have geographic range shifts, which means that some organisms are going to move more north, some are going to move more south. Some plants that are here right now in the Portland area are starting to die off because our weather systems are changing so much. You're going to have phenology shifts. So seasonal events are going to change, flowerings, hatchings. when you lose your winter coat or when you try and camouflage with the snow. Hopefully we'll have evolutionary adaptations, so the alleles in the populations that are more variable and able to adapt to change will start to change to fit in better with our climate crisis. And then we know this is happening, extinction. We're in the midst of the mass extinction right now. So the 6th extinction is happening. We're losing species at a rate of 100 to 1,000 times higher than the background extinction rate. We also talked about ocean acidification, deoxidation, so that's going to be a big problem. All of this is compounded and complicated by sea level rise and all the other threats to biodiversity, glacier retreat, all of that. This is our expected change in net primary production. Remember, net primary production is the amount of sugars available to the next trophic level. And we have increase and decrease, and you can see those patterns. Areas that are tropical wet forest and we're around the equator are going to have a decrease. And then we're going to see a little bit of an increase up by the poles. And that's because our temperature is shifting and our temperature ranges are shifting. So it's pretty interesting. Last, I have advice for the future and this slide, which is projections for the future. The major takeaway I want you to think about is it's not too late. Like, I know it's really easy to get discouraged and feel like everything is going horribly wrong, but we still can fix things. We still have power. We're not helpless. We can do something about this. So let's go through this graph. Here you have millions of years, then thousands of years, and then years into the future. So this is our timeline on the bottom. Then you have changes in atmospheric temperature. So temperature, not CO2 here. And then this is what we've recorded so far. Super variable changes in temperature millions of years ago. Then we get to thousands of years ago, and we have these highs and lows and spikes that we're used to. And then starting 10,000 years ago, because we're changing the scale, right? So these little spikes look more drastic because they're smushed in together. We're changing the scale, and we see it just kind of balance out. And then here's where we are today. So there are 4 options. If we continue to have really high emissions of greenhouse gases, you can see this red bar, here's the mean line. It's projected that we will increase the atmospheric temperature by about 7 degrees Celsius. If we do the opposite and we have a dramatic reduction in greenhouse gas emissions, it could be as low as 0.5. Like, that's awesome. That's totally awesome. And then if we did a little bit less, it could be around 2, and a little bit less, it could be around, what's that, 3.3 or something. So there's a range. We're not totally ruined yet. There's possibilities in the future, and we can do something about this. And so I want to end on this slide of personal choices to reduce your contribution to climate change. And so I know it's a little bit light colored on light colored background. And so this is based on cumulative emissions. So it's like an average. So your personal impact would be different. Then we have low impact, moderate impact, and high impact. And then the lowest impact is to upgrade your light bulbs to, not halogen anymore. Easy, cheap, and it costs less in the long run to do it. So if you haven't done that, I recommend that. Moderate impact is hang your clothes to dry instead of using your dryer. And I know it's hard when it's like humid and pouring rain in Portland, but during the summer, it totally works. And they smell nice and breezy then. Recycle, please, if you can. And be careful what you're recycling. In Portland, we have a habit of recycling things that aren't actually recyclable because we want them to be recyclable. So read the information packet that comes with your recycling carrier's container that you put it in. This is one I didn't realize until a couple of years ago. Washing your clothes in cold water saves a good amount of carbon dioxide, and it makes the color stay longer. So turn those jeans inside out and put it on cold. We wash everything in cold unless it's like a biohazard, and then it can get hot water to kill the bacteria. Replace your typical car with a hybrid. This is debatable now because we know that hybrid cars have batteries that have all this really intensive environmental impact materials, but either keep your beater on the road going well, that's not producing a ton of smog, or ride your bike, or think about your transportation is really what this option should be. Maybe if you know that your car is not going to pass DEQ, it would be a good time to invest in something that's more energy efficient. Then in high impact, we have eat a plant-based diet. So we've talked about cutting out beef before. Beef is such a contributor to methane and dehabitat destruction and water use. And it would be great if everyone would just eat a lot less beef. That would be fabulous for the environment. And there's health benefits too. Switch to electric car or no car. So that's our personal contribution to that largest chunk of greenhouse gas emissions of transportation. Buy green energy, see if there's a community aggregate that you could get into. Here, we're also relating things to transportation. So avoid one round trip transatlantic flight. I know that hasn't really been a possibility this last year, but flying is very carbon intensive. So if you could just avoid one flight, you're doing something pretty big for the environment. And I think that's a nice, impactful thing that we can do as individuals. If you could get rid of your personal transportation, that's great. And then this is the one that tends to be a little bit, like people don't like the way it feels when we say it, but have one fewer child. And that's not advocating for you to do anything with your body. You are in charge of your own body. You do what you want. It's your life. But notice that they even had to change the scale bar from 1 through 4 up to 60 because people produce carbon dioxide. So the less amount of people, the less amount of carbon dioxide. And we know that overpopulation is its own issue that we talked about during class. So that is the end of chapter 53, which means it's the end of our lecture together. And I hope you enjoyed it. Email me with questions and have a good day.